Good afternoon. Welcome to our lecture on applications of data science and software engineering. This week will be a bit special. So today I'm going to talk to you and we are going to discuss controlled experiments. And on Thursday we are going to attend Benevol. I'm going to share with you the link to the video conferencing solution as soon as I got it myself. So during Benevol, you can attend as much as you like, any talks you like. There's only one talk which you are required to attend, and it takes place exactly during our regular time slot on Thursday morning. It's a keynote by Michael Pradel. So what is going to happen with your weekly quiz? So we have several questions related to the topic of today's lecture. And during the keynote of Michael Pradel, we are also going to take notes and see what kind of task you can get related to the keynote. But let us start. So today we are talking about measuring as precisely as possible. And I'm going to see in a moment why I'm saying as precisely as possible. It is still part of our discussion of data collection. You might remember that we've been talking about data collection more or less since the beginning of this course, after a brief introduction of the first week. So we talked about surveys, we talked about interviews, we talked about repository mining, and today we are going to talk about controlled experiment. So controlled experiment is a research method which is most typically associated with laboratory experiments. It's not the only research method which is associated with laboratory experiments, but it's the only one we are going to discuss during this course. So laboratory experiments are quite common in empirical software engineering research. In fact, they are responsible for 35% of all empirical studies published in 2017 in the Empirical Software Engineering Journal. This percentage is second only to sample studies, which we've been discussing last week, both when we talked about surveys and when we talked about repository mining. So the popularity of laboratory experiments is not so surprising, right? You might remember this picture when we tried to see what research strategies give us maximum, in a sense. In the same way, sample studies can give us maximum generalizability, so essentially we want to hear all the voices. Laboratory experiments don't give this, but they do give us maximal measurement precision. So if you are interested in understanding the impact of variable A on variable B rather than some other variable, we would like to exclude as many variables as possible, and to do this we need a controlled environment. Controlled environment, this is what those controlled experiments are all about. So what we are going to do now, I am going to present two experimental studies, and then we are going to see what do we learn from those studies and how we can apply. So the first topic of our discussion is sentiment and emotion in software engineering. So this is a popular topic in software engineering quite recently. The inspiration comes from the machine learning community that has designed tools for identification of sentiment, meaning polarity, like positive or negative, attitude in general texts, and those techniques have been applied to software engineering text. Unfortunately, it turned out quite rapidly that general purpose tools are not working for software engineering. So let us see how those tools work. So in general, given a relatively short text, think about something like question on Stack Overflow, or a comment on GitHub during the discussion, or an issue reported on Jira. Those tools determine polarity. So polarity is one of the three values: negative, neutral, and positive. And the idea is that the tool can represent the attitude or the feeling that the writer has put into their text. This can in its turn be used in order to identify what people think about certain pieces of software, or how people work together, or how people see themselves and whatnot. So the applications are quite about. So here we see a couple of examples. For instance, the first example, I don't have to ensure that the class loader knows groovy classes. You must do that. So this is a very clear indication of anger. This anger is directed at their fellow developer, so it's a negative emotion. Another example of negative emotion is the next one. I tried the following and it returns nothing. So this is not really anger, this is more of a sadness, but it's still a negative emotion. And of course, the last one, yes, it was a horrible syntax error, sorry guys. So this is in this case, this emotion is very clearly directed at oneself, but it's also wrapped in a form of apology. So as I mentioned, multiple tools have been proposed in the literature, both general purpose tools and tools for specific for the software engineering domain. And the question that the study of Nicole Lavielle and her co-authors wanted to address was which tool is the best for which dataset. As you might remember from our discussion of research questions in lecture 2, this kind of questions, of course, require more careful phrasing. So, for instance, when you are talking about tools, the authors have considered 4 different tools which are on the slide. When it comes to the data sets, they have considered 3 different data sets. And then finally, to decide the notion of best, they have used a manual annotation. So there was a human being, or actually a group of human beings, that was manually annotating the statements from Jira, Garrett, and Stack Overflow to indicate whether those statements are positive, negative, or neutral. And then, if the tool has a perfect agreement with manual annotation, we are very happy. If one of the two indicates neutrality and another one is not indicating neutrality, we call it a mild disagreement. And a severe disagreement would be when a manual annotation identifies sentiment as being negative and the tool identifies sentiment as being positive, or other way around. So in this story, we already see two important elements of a controlled experiment. First of all, we have independent variables, also known as factors, which we can see as an input. So those are the variables which the experimenter can change. So instead of considering those 4 tools, the experimenters might have considered some other tools. And instead of considering those data sets, they might have considered some other data sets. The dependent variable, which is the output of our experiment, is something which can be expected to be influenced by the choice of the input variables. So in this case, we have tools and data source as 2 independent variables, also known as factors. And as dependent variables, we can, for instance, consider the 3 forms of agreement as 3 different dependent variables. For instance, percentage of perfect agreement, percentage of mild disagreement, and percentage of severe disagreement. So in general, if you are going to put it into a more scientific perspective beyond the software engineering world, we can think about an experiment as this kind of ergospirometry lab. So ergospirometry lab is intended to measure metabolic changes when a human being is performing a graded exercise on a treadmill. So the independent variable in this case is the exercise itself. So how hard is it to perform a certain movement? And then the dependent variable are represented on the computer screen, whatever they might be. So in general, we always have this separation between independent variables and dependent variables. Independent variables are inputs, things which the experimenter typically can manipulate, and we are trying to observe the dependent variables. So if you are going to read literature on experiments, there are two more words which are often being used in this context, and those words are levels and treatments. So levels are different values of an independent variable. So for instance, for the variable tool in the experiment of Nicole Novielli and her co-authors, there are 4 levels. And for the variable dataset, there are 3 levels. Combinations of individual values of different independent variables are known as treatments. So essentially, if you have 12 possible combinations, then we have 12 treatments. And now it is to you. So on the slide, you are going to see a text describing an experiment. And what I would like to ask you to do is to decide how many independent variables do you see in this story and how many dependent variables are there. And I'm going to start the poll. So I see 9 responses so far. Please go ahead and vote. A, 1 independent, 1 dependent. B, 1 independent, 2 dependent. C, 2 independent, 1 dependent. And finally, D, 2 independent and 2 dependent. Then you have an option for I'm not sure. I'm not sure whether the thing is, whether the polling of the big blue button allows for this. Just vote for the thing which you feel most comfortable with. Obviously, this is not graded. And actually, I cannot even see who is voting what. Okay, let us publish the results. So we got 1 A, 5 Bs, 3 Cs, and 2 Ds. So good news is that the majority has actually chosen the right answer, 1 independent and 2 dependent variables. So let us take a look at this story again. So in this experiment, the authors compare 2 diagram types, activity diagrams and state machines, to each other. This means that in fact we have 2 levels of 1 variable. So there is 1 independent variable, which is a diagram type. It has 2 levels, activity diagrams and state machines, and this is essentially a choice between the 2, which the authors or the experimenters can manipulate. So we have 1 independent variable. So what happens with dependent variables? For research question 1, the authors are looking at the number of errors made, and for research question 2, they're looking at the self-assessed comprehensibility. So there are 2 things that can be influenced by the choice of the diagram type. So For each one of the research questions, we have one independent, one dependent. In total, we have one independent and two dependent variables. So number of errors and self-assessed comprehensibility. Okay, let's continue. This is a second experiment. You might remember it from the first lecture. We talked about the study of fMRI to understand whether the code writing process and the pose writing process are similar in terms of brain area activation. So the research question here was, do different types of writing exhibit the same patterns of neural activity? This means that, of course, we have here code versus prose, which would be one variable. Another variable would be fill in the blank versus long response. You might remember that in the experiment, subjects have been offered two types of tests. They were either supposed to write a small piece of prose or a small program, which is what the authors called long response, or they have been given a sentence or a code snippet with some parts missing. This was the fill in the blank exercise. So the notion of type of writing is operationalized through two different independent variables. Dependent variables are expressed in those patterns of neural activity, and specifically Brodmann areas. So Brodmann areas are parts in our areas in our brain which are usually activated depending on specific cognitive tasks. So not surprisingly, the type of writing is what we can manipulate, what the researchers can manipulate. So those are independent variables, also known as factors. And the dependent variable is Brodmann area. Brodmann areas, Brodmann. But there is another category of variables. We don't want those variables to affect our study. But at the same time, from the previous literature, we know that those variables can influence the patterns of neural activity. So for instance, if you are left-handed versus right-handed, some of the areas in the brain activity will be just different. If you will be symmetrical, right? If you are a native speaker or a non-native speaker, your ability to write prose might be influenced. So somehow we need to there is a question in the chat. Why are we not considering the two types of writing as values of an independent variable writing type? We actually are, right? So there are two variables. One variable is code versus prose, and another variable is fill in the blank versus long response, because you can combine them in four possible, you can combine them in several possible ways. So you can do code and long response and prose and fill in the blank and so on. So the idea here is that we don't want to, first of all, we not always can manipulate variables such as left-handed versus right-handed, but we also do not necessarily want to study their impact on the dependent variables. So we always have those parameters. Parameters are variables that we can fix their values during the experiment. So in the study of Kruger, for instance, which is a study of this fMRI, the researchers have only considered native speakers who had a basic programming course as a background and that are right-handed. So in this particular way, they have excluded influence of the parameters on the dependent variable. However, this also means that the results of the study cannot be directly generalized to non-native speakers, to professionals, or to left-handed individuals. So the moment we are fixing parameters, we are losing generalization. And this is exactly this balance between control and generalizability we have talked about during the research strategies discussion. Okay, the third experiment. This image is a visualization of a software system. This visualization technique is known as code sitting. You see here several blocks, several buildings. The size of those blocks, size of those buildings is determined by variables associated with the source code. So for instance, the height of the building is a number of methods in a class. The base size is the number of attributes. And the color is presence of specific code smells. So if you look carefully at the slide, you will see that, for instance, yellow corresponds to brain class, and red corresponds to God class, and so on and so forth. This looks, of course, pretty, and we can clearly see some phenomena. For instance, we see that data classes are usually low, meaning that data classes have few methods, but quite a number of attributes. This is not so surprising because this is more or less a definition of a data class. But we still do not know whether this pretty visualization is useful. So the question that the researchers wanted to ask here is, which tool is the best for which system? Of course, asking which tool sounds kind of awkward, because at the first value of it, we only have one tool, namely the code sitting. But of course, developers are actually working without this tool, and somehow they are performing their daily programming duties. So it's very important to choose a baseline, which is essentially a starting point used for comparison. So in this particular case, baseline is either a tool, such as an IDE, or a manual approach, which is being used by software developers today to achieve exactly the same goal that the newly proposed tool is trying to achieve. So in this case, this baseline was Eclipse IDE. The researchers have chosen two systems, a medium-sized system finds bugs and a large system Azurias. And they have decided to involve human participants, give them a task or a series of tasks and programming tasks, and then to measure both correctness of the task, for instance, presence of bugs or absence of bugs, and the time required to perform the task. And again, the choice of the tool and the choice of the system are our independent variables. We could have considered different variables. We could have considered different tools. So we could have considered different tools, different levels of those variables. The dependent variable is something like correctness of the task and time required to perform the task. So again, we have two independent variables and two dependent variables. Again, there are some variables which might influence our results. For instance, we can have industrial participants versus students. We can also have beginners versus advanced users. And now we have a choice. We can consider those variables as parameters. In the same way as the study of Kruger of the fMRI has decided to focus on subgroup of our participants, of their participants. So if we are going to consider this industry versus academia and beginner versus advanced as parameters, then we will be necessarily focusing only on a subgroup, for instance, only at industrial advanced developers or only at beginner programmers from academia. The risk here is, of course, that we might actually end up having too few participants to make any meaningful observation. So an alternative would be to consider this as so-called undesired variation or a blocking variable. So we are going to see later on why those variables are known as blocking. But for now, blocking variables represent undesired variation which we cannot control and we cannot exclude. Okay, there is a question in the chat. If we don't choose external variables, what is the negative outcome? What if we negative outcome? If we don't choose blocking variables, what is the negative outcome? I'm not sure that I understand what you mean by negative outcome. Okay, maybe you can try to ask me during the break or something, or on maybe you can ask to ask it on Slack. Nathan, maybe you can try to see what's going on Slack, right? Okay, let us continue. So this is a small story from the book of Natalia, Juristo, and Ana Moreno. I'm going to use it for the lecture of today. It's a story of an aeronautics software development laboratory. And the task for you to identify independent variables, dependent variables, parameters, and blocking variables. So there are 4 types of variables in this story. The question is, as usual, A, B, C, D. Let me start the poll. And we are going to see the detailed answers on the next slide. So let me recapitulate. So independent variables are inputs. This is something which researchers can manipulate. Dependent variables is the output, is what researchers ultimately want to observe. Parameters are fixed. For instance, all participants are native speakers or all participants are right-handed. And blocking variables are those where we cannot somehow fix this diversity and we need to embrace this variation, which is even so it might be undesirable. So we have 9 responses. Please continue. Okay, so it seems that the most popular answers are A and C. So let us look at A. Dependent is a programming language, blocking are the programs. So I have to disappoint you. So what the study is essentially trying to do, they're trying to identify the best 2 or 4 possible programming languages in terms of productivity. So what they essentially can manipulate, what they can influence directly is a programming language. what they want to observe is productivity. So this means that independent variable is a programming language, dependent variable is productivity. So this means that options A, where programming language is called dependent, option B, where productivity was called independent, are out of the options. So it's now only C or D. So to figure out what is going on, we need to read further. What do we see further? So we see that we have a task. So two programming languages will be used to implement two versions of the same flight control application. And if you read a little bit further, we see that there are 30 modules with similar functionalities. So the same application and similar functionalities are parameters. So C looks promising, but we still don't know whether it is the right one because we have not looked at the programming yet. And we didn't look at the programmers yet, sorry. So what do we know about the programmers? The only thing we know about the programmers is that there are 12 of them. There is no indication that those programmers are all interchangeable. So there is no indication that they all have the same level of experience or the same training or the same whatever. They are what they are. We cannot focus on developers having specific level of expertise, specific training, specific experience. They are what they are. This means that this is an example of undesired variation. So programmers are a blocking variable. And this is exactly option C. So let me show you a slide where the 4 types of variables are highlighted. In black, we see the independent variable, so it's possible programming language. What is it supposed to influence? Productivity. Blue, dependent variable. The same flight application, the same flight control application, sorry, the same functionality are parameters, and finally programmers are whatever they are, so it is blocking variable. And there is even a sentence saying that the individual productivity of each programmer differs, which could affect the experiment productivity. Okay, so let us look further. Of course, experiments can be designed in many different ways, depending on how many variables of each kind do we have. So in the simplest case, we have one independent variable or one factor, and all parameters are fixed. This is so-called one-factor design. At another extreme, we have many independent variables with many alternatives. We have undesired variations, which are blocking variables, and we get blocked factorial design. The book I'm using here is by Natalia, Juristo, and Moreno, Basics of Software Engineering Experimentation. You might find similar books related to other kinds of experimental design outside of the software engineering field. And as you can imagine, since there are entire books dedicated to this subject, I cannot aim to cover this topic extensively. The goal of this lecture is to introduce you to the field, such that if you will be required to conduct a controlled experiment as part of your project for this course, if you choose to conduct a controlled experiment as part of the project for this course, or if you are required to conduct a controlled experiment, for example, for your master project, so that you will at least know what those words mean and what kind of options you have when designing an experiment. Again, for further details, I would like to refer you to the book of Juristo and Moreno. So we are going to start with the left-hand side. So we are going to start with a situation when we have one independent variable. And this main idea, and actually the only idea of simple randomized design, which is essentially what the first way we are going, the first type of experiment we are going to consider, is that we are going to assign the alternatives to experiments in a random way. So alternatives are factor levels. So for instance, if we have a choice between find bugs and check style, we can always allocate them to different projects using a random assignment. The word random here is crucial. We need to be careful because randomness cannot be assured by means of human assignment. Because human assignment is believed to have an underlying cause. Whether this cause is conscious or subconscious, this might jeopardize randomness of the assignment. You might remember that we've been talking about it when we talked about random sampling. Again, randomness should be true randomness. Throwing a dice, taking cards out of pack. So this is a true randomness. So in this experiment, what was going on, we have 10 projects. We would like to analyze presence of undesired coding features using two similar tools, find bags and check style, and we decide to use a card deck as our randomness generator. If the card we fetch from the card deck is red, we assign find bugs, and if it is black, we assign check style. This is simple randomized design. In case of only two alternatives, this design is also known as A-B between subject. Of course, in general, the simple randomized design can work for any number of alternatives. But if there are only two, then those options are usually called A and B, and each subject is randomly assigned either to A or to B. This is a very popular experimental design. Facebook, for instance, is using it continuously to understand how the Facebook users respond to changes in the interface and new functionality being offered. And moreover, Facebook actually offers A/B between subject designs to external users, to businesses that might be interested in running this kind of tests for their own purposes. But of course, since it's essentially a project and a tool, why wouldn't we just run all tools on all projects? So find bug and check style on project 1, the same for project 2, and so on and so on. This is what is known as paired one-factor design. So it's no longer simple random, there is no randomness involved at all. It's a paired one-factor design. In a sense, it's exhaustive, right? This is how one-factor design would look in practice. So the columns correspond to different log parsing techniques, SLCT, AEL, IPLOM, and so on. And the rows correspond to different data sets. While this table reports results for individual data sets, we are not interested in them. The only thing which we are actually interested in is the overall performance, which is summarized in the last row. And this row is called average. So in this particular case, we see that the best results are obtained by a tool called drain, and the worst results are obtained by a tool called logseek. Whatever this might mean, it doesn't matter, as long as we know that all those tools have been applied to all those data sets. Again, if we have only two options, we can also have this A-B design, but as opposed to the previous one, this was an A-B within subject. So every subject, which is in this case a project, experiences both options. A and B. So in a sense, both options are within the subject. What would happen if we would like to study how developers work with those tools? So essentially, if instead of talking about project 1 to project 10, we are going to talk about developer 1 and developer 10. So we are just going to do the same. We give them the same subsystem. We still have only one factor, so we are only having one subsystem. And we are going to ask them first to use find bugs, then to use check style, and we are happy. What would go wrong with this design? Please type. Actually, looking at the screen, at the time, sorry, I think it's better for us to stop now. Then we have the entire break to think about what can go wrong with this AB within subject design when applied to human beings. And we are going to reconvene at 2:25, so 5 minutes before the regular schedule. And so please continue typing, and I'm going to stop the recording. So let us start. You might remember that before the break, I have asked you to think about possible problems with one-factor design when applied to human subjects. So we have 10 participants, 10 developers, developer 1 to developer 10. We have two tools such as find bugs and check style. And the idea would be to ask the developers to analyze the same subject system using those tools. First of all, find bugs and then check style. So I've asked you what could possibly go wrong. And so far I have one answer by Rika Yan, who said that the scalability might be an issue. I'm not sure why scalability actually be an issue, given the fact that we essentially are giving those tools to our developers, and the assumption is, of course, that each one of those tools can be applied without any problems. Time consuming. Yes, indeed. Running two tools and performing analysis of two tools will take more time than, of course, running them once. That's true. They might give less attention to the second part, says Mika. This is very true. This is a phenomenon which we usually call fatigue, when people are simply getting tired as the experimental task progresses. Another thing which can happen is that developers can learn. Of course, find bugs and check styles are different tools, but they are essentially addressing similar concerns. So they might be detecting the same kind of problems that the system has. So once I have found those problems using find bugs, I don't really need to use check styles to recognize the very same problems. So this is why usually when we are talking about paired one-factor design with human subjects, we use randomization, but we do not randomize who is doing what, because both people are both groups of people are going to use the same tools, but the ordering of those tasks. So essentially 50% of the participants will start with find bugs and continue with check style, and 50% other participants will start with check style and then continue with find bugs. So this kind of design is known as a counterbalance design. So we have 50% starting with one, 50% starting with another. And of course, we don't really need to, so and of course, we're going to use randomization to allocate people to each one of those two scenarios. So if I'm fetching a red card, then it will be first red find bugs and then black check style. And if I'm fetching a black card, all the way around. So we can also write this design as follows. Essentially here we have two possible scenarios: first find bugs and then check style, and then first check style or find bugs. So far everything was as nice as possible. There were no real undesired variations, there was no parameterization, and we only had one factor. So let us make our story a little bit more complicated. So we are going to look at a simplified version of our code city experiment. So we are going to look at one factor, so namely the tool which has been used, and one blocking variable. So we are going to distinguish between industrial and academic participants. So what we can do, we can create 4 groups. Each value of an independent variable will then be combined with each value of a blocking variable. So group 1 will be, for instance, code city and industry, and group 3 will be Eclipse and industry. The choice between code city and Eclipse, of course, happens randomly, but there is no real choice between industry and academia because people either from the industry or from the academia. We can also write down this as shown on the right. And this doesn't really mean that the same person first should work with Code City and then with Eclipse. This simply shows that some people from the industry work with Code City and some others with the Eclipse IDE. And this is where we can finally understand why those variables are called blocking variables. Each row of this matrix, or each value of the undesired variable, is called a block. The number of experiments per block is given here by respective columns, is what is called the block size. Yasona says that he sees the same slide. It's probably not the same slide, there's minor modifications. So the next slide will be different. If you still don't see it, please type in the chat. So if we are moving to a more complicated scenario, when we have 2 undesired variations, then we ultimately might need to consider all possible combinations. So industry and advanced and code city, or academia and beginner and Eclipse. So this is essentially what is going to be called full factorial design. And as you can imagine, this kind of designs become prohibitive quite rapidly. The more variables we have and the more levels each variable has, the more possible experiments we need to conduct. And of course, typically for each experiment, we need multiple people participating in it because we want to exclude interpersonal differences. And this is where it becomes really, really prohibitive, really, really fast. So an alternative solution would be to consider the following design. So in this case, you see that every row and every column contains a tool choice, and it contains it only once. So both beginners and advanced user experiment with Code City and with Eclipse. And in the same way, both industrial and academic participants use both Code City and Eclipse. So in a way, if you assume that there is no interplay between the level of experience and industry versus academia, we do not really need to explore all possible options, as long as we can argue that every subpopulation with respect to that every level of our every independent variable has been associated with a specific tool and with all those specific tools, right? So this design is known as a Latin square design, and more specifically 2 times 2 Latin square design in this case. So in a Latin square, we have every row corresponding to different numbers, and every row containing different numbers, and every column containing different numbers, and each number appears only once in every row and in every column. So how does it work in practice? And this is an example of a study that has focused on test case prioritization. So what is a test case prioritization? Usually, if you have lots and lots of test cases running against your system, running all of them becomes prohibitively expensive. So every time you are introducing a change, there should be some kind of magic happening, which determines those or those tests should be executed. So those and those tests have a priority. And of course, the baseline here is a manual assignment, the manual recognition of what tests should be prioritized. And ideally, we want to have some kind of automated tool to support this decision making. So in the study by Lucas Lima and his co-authors from Brazil, the authors have considered one independent variable, which is the choice between manual or automatic test prioritization technique. However, there are different testers, X and Y, and different suits, 1 and 2. So in order to identify benefits and shortcomings of manual versus of automatic test prioritization versus the manual one, the authors opt for a 2x2 Latin square design. So as you see on the screen, tester X applies manual prioritization to a suite, and tester Y does the same. And in the same way, tester X applies automated test prioritization, and the same for tester Y. And in the same way for suites 1 and 2. Of course, this is a way to organize your experiment if you assume that testers and suites are independent from each other. And in this particular experiment, we only had 2x2. So we had only 2 options for each one of the axes, for testers and suites. In general, it works for more levels than 2. Here we see a 7x7 Latin square, and this Latin square comes from a stained glass window commemorating British statistician R.A. Fisher in the dining hall of Gonville and Caius College in Cambridge. So this Latin square was featured in Fisher's book, The Design of Experiments, and as you can imagine, this book was highly influential for this field of designing experiments. And we are also going to see the name of Fisher in a later lecture when we are going to talk about quantitative analysis. So Fisher was an influential statistician and designer of experiments. Still, Latin squares, 2x2, 7x7, whatever by whatever, only work for 2 blocking variables. What can we do if we have more? So we still have 1-factor design, but this time life becomes a bit more complicated, and we have 3 undesired variations. Blocking variables 1, 2, and 3. The smart idea here would be to take 2 Latin squares, A, B, C, D, on the left-hand side and Greek denoted square on the right-hand side, and combine them such that in this combined square, every row and every column has every Latin character. Every row and every column has every Greek character. And every cell has a unique combination. So this combination is known as Greco-Latin square. So this means that essentially, instead of looking at all possible experimental designs, we are merely looking at 16. Thinking about it, you might recognize that not every pair of Latin squares can be combined in such a way that every cell has a unique combination. If such a combination is possible, then Latin squares are called orthogonal. So how does this work in practice? This is a study from Umuhoza, Brambilla, Piramonti, and Cardot. And this is a study of simplification of business process modeling languages. So T1 to T6 are 6 design tasks. Just to give you a feeling what a design task could be, it is something like, for a real-time stock monitoring dashboard, identify middleware technologies which scale to more than 100,000 users. Or something like, you have an online shop, it is implemented in Java, it exposes services to other apps. So what are the best practices related to service decomposition to achieve high cohesion and low coupling? N and E here correspond to different approaches. So N is a normal approach, which is used as a baseline, essentially use keywords and search for solutions. E is an enhanced approach proposed by the authors. So what do we see here? We see here that we have a kind of blocky structure, which is reminiscent of the Latin square we've been talking about in the beginnings. It's kind of 2 times 2, but it's not exactly 2 times 2. Because if you see the gray, so the rectangles with the gray background, they are all about the normal approach. The rectangles with the white background, they are all about extended approach, enhanced approach. Each participant is performing 6 tasks, 3 normal, 3 using enhanced approach. And the ordering of those tasks is also rotating. So you are starting with T1 if you're participant 1, and then the next one starts with T6, and so on. The strange thing is that while this is definitely an interesting design, it's strictly speaking not a Greco-Latin square, simply because it's not a square. If you look at it carefully, you will see that it is 6 times 12. And in fact, Greco-Latin square on the size of 6 times 6 does not exist. So as you might remember, I mentioned that in order to obtain a Greco-Latin square, we need to have 2 Latin squares of the same size, 6 times 6, which are orthogonal. And those are not existent. And this is a very strange story. So this statement that such a 6 times 6 Greco-Latin square doesn't exist goes back to Euler, who conjectured this in 1779. And in fact, he has conjectured that this kind of squares do not exist for any number which can be written as 4k plus 2. So essentially 6, 10, 14, and so on. And we had to wait for more than 100 years till Gaston Tari published a proof confirming the validity of Euler's conjecture for the order of 6. What's interesting is Tari was essentially not a mathematician. He was an amateur. So if you see, right, I mean, if you are liking something, then you don't necessarily need a formal training if you have passion. And we had to wait for yet another 50 years to see that the hypothesis of Euler about 4k plus 2 does not really work. Parker, Bose, and Trihande have constructed methods for building those Greco-Latin squares of order 10, 14, 18, and 22. And of course, Parker has used UNIVAC. So unfortunately, I could not find an image of Ernst Talden Parker, so it's just a random guy standing next to Univa. So this is how you see how this story has unfolded for almost 200 years. But let's get back to our experimental design. So we agreed that if you have an undesired variation, you have two undesired variations, you have Latin square. If you have three undesired variations, we have Greco-Latin square. Theoretically speaking, if we have even more undesired variations, we can think about hyper Greco-Latin squares, using even more basic Latin squares and combining more basic Latin squares together under the same constraints as in case of Greco-Latin square, namely every row and every column has every Latin character, every row and every column has a Greek letter, and every cell has a unique combination. This being said, those are extremely complicated designs. So before going there and before conducting your study using hyper Greco-Latin design, please reflect on whether you really need all those variables. Maybe you can consider some of those blocking variables as parameters, and maybe you can fix them, essentially reducing the prospective pool of participants in favor of higher degree of control. So let us move to the second part of this story, and let us move to the situation when we have k independent factors, and each one of those independent factors has n alternatives. So again, here there are all kinds of variants. I'm not going to discuss all of them, but at least I hope to give you the first understanding how those experiments can be conducted. So if you have a two-factors design, which is essentially the case for our code city experiment, so we have tools and we have systems. One of the classical approaches would be so-called one at a time. It's a simplest technique, and it is essentially focusing on the argument that if our variables are independent, then we can consider them in isolation. So we are going to fix randomly the values of all factors but one. We are going to vary the values of this particular factor. We are going to observe the best solution, whatever best might be in terms of dependent variable. We are going to fix the value of a factor corresponding to this best solution. And then we are going to release another factor and vary another factor. So in terms of our example, how would it work? Let's say we are going to first of all focus on find bugs, and we are going to decide whether Code City or Eclipse is better. So assume that Code City is actually better. And then we are going to fix Code City, and now we are going to try to apply it to find bugs and Azurius. And in this case, let's say we assume that Code City and Azurius is better. However, we don't really know that Code City and Azurius is really the best combination, since there is a version of Eclipse and Azurius we have not really considered. We cannot be sure, of course, but the main point here is that one at a time reduces the full factorial design, which is essentially a product of the number of levels for each one of the independent variables, to sum of those numbers of levels. This is why when conducting a full factorial design is not an option, simply because we cannot get sufficiently many participants, we cannot run sufficiently many tools due to some kind of memory considerations or runtime considerations or whatever, we might consider one at a time. At the same time, one at a time is, of course, heuristics. So there is no guarantee that it will produce most plausible results. So what else can we do in order to somehow avoid doing a full factorial design, but doing a little bit more than one at a time? So a possible improvement will start with binarizing every factor. So essentially this means that we are reducing the number of levels of every independent variables to 2. Instead of talking about small, mid-size, large, and extra-large systems, we are going to group small and mid-size to small, and large and extra-large to large. Instead of distinguishing between systems of different ages, we can just focus on all versus new. Then we can execute a full factorial study on this binarized data. So this essentially means that we need to compare 2 power k alternatives, where k is a number of factors. 2 power k is still huge, but it somehow sounds better than n power k. Once we have completed this step, we can identify which factors seem to be of little influence on the dependent variable. And let's say we keep f factors left. So essentially what we are doing, we are saying that if for a certain factor, it does not really matter for our dependent variable whether we are using old or new, it will not make any sense to make a more fine-grained distinction between very old, moderately old, and very new systems. So if the coarse-grained distinction between the levels does not show any impact, or does show little impact of the dependent variable on the of the independent variable on the dependent variable, then it doesn't make sense to consider more detailed distinction between the levels. Once we have done this, we can run another full factorial study. This time we are going to use original levels, but this time we are not going to include every factor, but only those factors that have been found influential in the previous study. So essentially we have 2 reduction steps. In the first reduction step, we are temporarily reducing the number of levels to 2 in order to eliminate some independent variables. And at the second step, we are restoring the original levels, but only for factors, for independent variables, which have been shown to be influential. This kind of improvement is known as fractional factorial design. So this is one possible method to conduct a fractional factorial design. There are more. If you are interested, I can refer you to the book of Juristo and Moreno. So those designs are known to save time and money, but of course at the expense of providing less information than full design. Specifically, we can get some, but not all, interaction between the factors. So in particular, if we have reasons to believe that there can be interactions between factors, full factorial design will expose all of them simply because it considers all possible combinations. Fractional factorial designs are less likely to do so. Of course, if we have good reasons to assume that there are no interactions between some factors, or that interactions between some factors are negligible, since there is no real drawback. So the question is, what do you know about your domain before designing your experiment? So just to give you a point related to explain this idea of interactions, let us consider the following situation. So here we have two independent variables, so two factors, A and B, and we have a blocking variable C. And let us, for the sake of simplicity, assume that we have three cases with a dependent variable producing values of 10 and 15 in every case. If we are in case, so let us start with case 1. If we are in case 1, then we know that for the first two situations, A1, B1, C1, and A21, B2, C2, the variable was 10. And for the remaining two situations, the dependent variable was 15. So we can conjecture that A influences the dependent variable and B does not. So essentially we can say whenever A is A1, then the dependent variable is 10. Whenever A is A2, the dependent variable is 15. And it doesn't really matter how the factor B behaves. Let us look now at case 2. In this case, using the same argument, we could conjecture that B influences the dependent variable and A does not. So indeed, if B is B1, then the dependent variable is 10. And if B is B2, then the dependent variable is 15. And in the same way, it does not seem to matter what the variable, the value of the variable of the factor A is. Finally, let's look at case 3. In this case, we have again 10 and 15, but 15 occurs in the first row and in the last one, and 10 in the second one and in the third one. What could be the reason? What could we conjecture about the influence of our factors? We could conjecture that if A is A1 and B is B1, or A is A2 and B is B2, then the dependent variable is 15. Essentially, we could conjecture there's some kind of interaction between A and B that leads to this value of 15. Or we could conjecture that this is essentially not so much about the factors, but about blocking variable. So if the blocking variable is 15, C1, sorry, then the dependent variable is 15. And blocking variable, recall it again, it is not something we can control. It's an undesired variation. So this means that in this particular experiment, we cannot distinguish between the impact of the blocking variable of this undesired variation and the interaction between A and B. So to address those challenges, you are supposed to be performing a blocked factorial design. So blocked factorial design can identify blocking and the corresponding confounding situations, such as the confounding of the blocking variable C and the interaction between A and B in the example we have been looking at. There is an entire theory of how to construct those block factorial designs. However, discussing it as part of this course would really go beyond the scope. This is not common in software engineering, but it is important for you to know that this kind of situations might occur. You should be aware of them, and should you be interested in designing this kind of experiments, there is a literature you might consult. Either this book of Juristo and Moreno I already mentioned, or general books on design of experiments. So what have we done today? So we have talked about controlled experiments. we have seen that participants of those controlled experiments can be human beings, such as was the case in the study of Kruger with this fMRI scanner, or systems, which was, for instance, the example of a study from Nicole Novielli on sentiment analysis tools. We have seen that designing controlled experiments requires understanding of different types of variables that play a role in this, in what we want to evaluate. So those variables are independent variables, also known as factors, parameters, blocking variables, also known as undesired variances, and dependent variables. So just to remind you, independent variable is an input, it's something which we can influence. This is the variable we actually want to understand how it affects our dependent variables. In this example of aeronautic software development lab, an independent variable was a programming language. Dependent variable is what we want to observe. In this example, it was productivity. In the study of Kruger, those were brain areas, brain activation areas. In the study of Novielli, it was percentage of agreements or percentage of disagreements. So those are typical dependent variables. Two types of variables play an additional role, and they can intervene in the relation between your independent variables and dependent variables. Those are parameters and blocking variables. Parameters are things you can influence by fixing them. So for instance, you can only consider non-native speakers or only native speakers in the fMRI study. In this example of the aeronautics, we are talking about 30 modules with similar functionalities. The functionality is similar, and we are talking about the same kind of application. Blocking variables cannot be fixed, either because it is physically improbable, that you really cannot, or because it will lead to substantial loss of data points, which might threaten the experiment itself. So in this particular example, if you have 12 programmers, then they are whatever they are. We cannot focus on, we cannot select a smaller group of those programmers with similar experience or similar training, because this might lead to losing too many programmers. Finally, there are different ways of designing those experiments. We have seen one independent variable, we have seen multiple independent variables, and an interplay between those things and variations versus parameters. So since this was the last lecture on data collection, I thought I will also give you a small recap of the topic. So when talking about the data collection, we have discussed 4 different data collection techniques: interviews, controlled experiments, repository mining, and surveys. These data collection methods are predominantly related to research strategies as field studies, laboratory experiments, judgment studies, and sample studies. Beware, those research strategies can be and likely exploit additional data collection methods. If you are interested in a judgment study, you will typically not only conduct an interview, but you will also conduct a focus group. If you are interested in a field study, then usually an interview is not enough and you want to conduct a case study. If you look at the papers which Stoll and Fitzgerald have analyzed, so those were all papers which have appeared in the Empirical Software Engineering Journal in 2017. you might notice that the research strategies we have been talking about cover 95% of the studies. So laboratory experiment, which is typically associated with controlled experiment, sample studies, which are typically associated with surveys and mining repositories, judgment studies and field studies are most often associated with interviews. The only 5% we have not talked about are related to experimental simulation. So how our life will look in the coming lectures and in the coming weeks. So on Thursday, we will have a keynote by Michael Pradel at Benevol. As already mentioned in the beginning of the lecture, I'm going to share with you the link to the virtual event as soon as I have received it from the organizers. If you are interested in the topic of software evolution or in the topic of empirical software engineering, I would like to strongly encourage you to look at the program and select the topics and the talks you might like and just attend it. Participation is free. And I don't know how often you have you attended scientific workshops. Okay, there is a question. I emailed for registration myself already for Benevol. Is that fine? Yes, it is fine. The choice is yours, right? Essentially, if you email them, you will receive a link with the to the video conferencing solution directly. If you did not register, they will just notify me and I will share it with you. The only request from the side of the organizer is, please be a bit reasonable and a bit careful with this kind of links. Nobody wants to be Zoom bombed. This will also conclude our discussion of data collection techniques. So, as I promised, the second part of the course will be related to data analysis. So we have collected our data using different mechanisms. The question is, what are we going to do with this data? And of course, there are different kinds of data analysis techniques. Some of them are pretty much independent from the data collection. Some of them are more closely geared towards specific methods of data collection. But for example, if you are getting textual input, it can be coming from a survey, it can be coming from a interview transcript, it can be even coming from a repository if you are looking at, for instance, code review discussions. So all these kind of data can be, for instance, analyzed in a qualitative way. So what are we going to do? So next week, Tuesday, I'm going to talk about quantitative analysis, and on Thursday, Dario Dinucci from JETS is going to talk about applications of machine learning to analyze software engineering data. The week afterwards, we are going to see qualitative analysis by Damian Tamburi, also from JETS. We will also see visualization. You might remember that one of the studies we have considered used visualization as an analysis technique. So we'll have a guest lecture from Germany, from Fabian Beck, who is an expert on visualization of software engineering data. I will talk to you about threats to validity of empirical studies, because of course, whatever we are doing can go wrong despite our very best efforts. And the last lecture will be by Michaela Keiler, who is consultant. So she is going to talk to us about using empirical software engineering in her industrial practice. This concludes our lecture. I will see you on Thursday, and please stay tuned on Slack for further announcements related to Benevol. Bye.